Okay, we're going to start chapter 2. We still haven't gotten any chemistry yet. We're building up to it. So the structure of the atom in the periodic table. So the atom is the basic structural unit of an element. It's the smallest unit of an element that retains the chemical properties of that element. So an atom of gold has all the properties of gold. And that's the smallest unit of gold that there is. So atoms consist of three primary particles: electrons, protons, and neutrons. The nucleus is a small, dense, positively charged region in the center of an atom. The nucleus contains protons, which are positively charged particles, and neutrons, which are uncharged particles. Protons, P, positive. Or proton walks into a bar, asks the bartender for a drink. Bartender says, "Are you sure?" Proton says, "I'm positive." Neutrons are uncharged particles. Think of neutral. Neutrons in the same bar having a drink, has a drink and asks the bartender, "How much do I owe you?" Bartender says, "For you, no charge." Okay. The electrons are negatively charged particles located outside of the nucleus. The protons and electrons have charges that are equal in magnitude but obviously opposite in sign. So a neutral atom has no charge, therefore has an equal number of protons and electrons. So electrons move very rapidly in a relatively large volume of space, while nucleus is small and dense. So if you picture a football stadium, you can picture the electrons going in the seats, the outer seats. The nucleus would be the size of a grape on the 50-yard line. So most of the mass of the atom is in the nucleus. Most of the volume comes from the electrons orbiting around the nucleus. When you look at the periodic table, you see a symbol of the atom, in this case it's X, a mass number called A, atomic number Z. The atomic number Z is the number of protons in the atom. And you can see it starts with 1 for hydrogen, 2 for helium, 3 for lithium, and it just keeps going up in order, one by one. The mass number is the sum of the numbers of the protons and the neutrons. So hydrogen has a mass of 1.008. We'll talk about why that's not an even number. So to get the number of neutrons, you take the mass number and subtract the atomic number. So for hydrogen, exactly, the mass number is essentially 1. Subtract the number of protons, which is 1 from the atomic number, which gives you 0 for neutrons. Carbon has an atomic number, mass number of roughly 12, atomic number of 6, so 12 minus 6, it has 6 neutrons. Fluorine has a mass number of 19, an atomic number of 9, it has 10 neutrons. If you look at a periodic table, out of the two numbers, the mass number is always going to be the highest of the two, and very seldom is it a whole number. So the mass number is the number of protons and the number of neutrons. The number of neutrons is the mass number minus the number of protons. So it's A minus Z. The number of electrons is the same as the number of protons. Now, even though the electrons have weight, it's negligible compared to that of the protons and the neutrons. So we usually don't include those in the mass calculations. So the electrons have a charge of -1. A mass in AMU, AMU stands for atomic mass units, of 5.4 times 10 to the -4, and a mass of grams of 9.1 times 10 to the -28. Protons have a charge of +1, an AMU mass of 1, and grams 1.67 times 10 to the -24. Neutrons, like I said, no charge, mass of 1, mass in grams of 1.67 times 10 to the -24. So you see the electrons are negligible. It'd be like going into a grocery store and putting 10 watermelons on the scale and getting a weight, and it says, wait a minute, tossing 5 raisins on there. Scale rating is not going to change any. So the electrons are like the raisins. Mass-wise, they're negligible. So here we have boron. How many protons? 5. How many electrons? 5. How many neutrons? 6. 11 minus 5. Iron. How many neutrons? Uh-oh. Advanced level math. How many? 29 neutrons. How many electrons? 26. How many protons? 26. That's all there is there. Isotopes. Atoms of the same element having different masses. How does that happen? They have the same number of protons. The number of protons tell you what element it has. If it has a different mass and has the same number of protons, it has to have a different number of neutrons. So hydrogen has 3 isotopes. 1 proton, no neutrons. 1 proton, 1 neutron. 1 proton, 2 neutrons. So you have hydrogen, deuterium, and tritium, which is radioactive. So if you look on the periodic table, it says the mass for hydrogen is 1.008. That results from the weighted average of all the isotopes of hydrogen. Most of it is hydrogen 1, a small percentage of it is hydrogen 2, and even smaller percentages of hydrogen 3. So if you do a weighted average, you come up with 1.008. So isotopes of the same element have identical chemical properties. Some are radioactive. If you look at chlorine, atomic number 17, the mass is 35.45. That's not the mass number of an isotope. That is the weighted average of all the isotopes. Chlorine consists of chlorine 35 and chlorine 37 in a 3-to-1 ratio. So the weighted average so if it's 75.77% chlorine 35 and 24.23% of chlorine 37, you convert the percentages to a decimal fraction. 75.77 is 0.7577. 24.23 is 0.2423. Changing decimals, or percentages to decimals. So to do the weighted average, 0.7577 times 35 is 26.5. 0.2423 times 37 is 8.97. Add them together, 35.5. That's how they figure out the masses in the periodic table. You see carbon is 12.011. Excuse me. So that's a combination of carbon 12, carbon 13, and carbon 14. So neon has 3 isotopes, and those are the abundances. So again, you'd make decimals out of the percentages. So there would be 20.0 times 0.9048 plus 21.0 times 0.0027 plus 22.0 times 0.0925. Whatever that comes out to be. Well, to go from a percentage to a decimal, you divide by 100. So you move a 2. So 90 would go 1, 2. This would go 2, so there's 1.0027. This one would go 2, so here's 1.09. Excuse me, that would be good on the recording. Okay. So you just figure out all of those and add them up. And you should come out with something for neon close to 20.180, which is the weighted average. Questions? Okay. AMU, exactly. Atomic mass units. So how did we come up with what an atom is? Can't see them, at least not until recently. So how do you know what you're looking at? Well, Dalton looked at different experiments. He only took atoms of element X, reacted them with atoms of element Y. He always got the same compounds in the same proportions of X and Y. So his theory was all matter consists of tiny particles called atoms. An atom cannot be created, divided, destroyed, or converted to any other type of atom. Well, we know today that that part's not true. We can destroy atoms. You know, we smash atoms all the time. Atoms of a particular element have identical properties. So we know all the atoms of gold have gold properties, all the atoms of lead have lead properties. Atoms of different elements have different properties. Atoms of different elements combine in simple whole number ratios to produce compounds, which he said were stable aggregates of atoms. So, you know, hydrogen plus oxygen always gives us water, H2O. Sodium and chlorine gives us sodium chloride. Chemical change involves joining, separating, or rearranging atoms. So those postulates, 1, 4, 5, and 6, are still regarded as true. 2 and 3 aren't really regarded as true anymore. So how do we know an atom just wasn't a single ball or whatever? Electrons were the first particles to be discovered using a cathode ray tube. And this is a cathode ray tube. You apply a high voltage, you have a cathode and an anode. You shoot particles. You have a magnet. The magnet, some particles go straight through, some get deflected. They're being pulled towards one of the poles. That tells you the particle is charged. How many people have seen a cathode ray tube? Y'all have. Oh, sorry, that was the southern slipping out. Y'all. You all have. I'm down here too long. Okay. So we have this, and it goes up. This, it goes up. There's a screen here. And these beams go, and a magnet rasters that beam up and down the screen, back and forth, and down and back and forth, real fast. And when it hits the screen, it lights up. You've all seen them. You've all looked at them. It's a television screen. The old television screens, the picture tube, is a cathode ray tube. The old computer monitors, remember those old big heavy suckers? Those are cathode ray tubes. That's the screen in the front, and that big heavy thing coming in the back, that's the back part of the cathode ray tube. The electrons raster back and forth, hit the screen, which has fluorescent material on it, and it lights up, and it goes back and forth so fast that it just looks like an image to you. If you've ever seen a movie on TV, and in the movie there's a television in the background, and you can kind of see this black line scrolling down the TV, that's because the way they film the movie is a different frequency in which the way TV operates, so you're picking up the rastering. Which is a little bit different than our digital TVs work today, the flat screens. So I think you're all probably old enough that you've seen a cathode ray tube or an old television screen. I know the day's coming when you guys people won't remember that anymore. I just saw something posted where they had two teenagers and they told them to dial a number using a rotary phone, and they couldn't do it. They had 4 minutes to dial the number. They couldn't figure out how to do it. If they've never seen a rotary phone, God, I feel like an antique, okay? So, technology is moving very quickly. Maybe too quickly, but that's right. How they discovered electrons. Protons were the next particle discovered by Goldstein. So they had the same charge as an electron, but opposite in size. It's almost 2,000 times as heavy as an electron. Neutrons were postulated to exist in the 1920s, but not demonstrated to exist until 1932, about the same mass as a proton. So now we have the three subatomic particles, protons, electrons, and neutrons. But how are they arranged? Again, you could just think of a whole big mishmash put together, protons, electrons, and neutrons. So initially, assume the protons and neutrons were uniformly distributed throughout the atom. Rutherford's gold foil experiment led to the understanding of the nucleus. So what he used were alpha particles. Alpha particles are essentially a helium nucleus. No electrons, just a nucleus. And he had put a piece of gold foil, and around it he put X-ray film. And he bombarded the gold foil with alpha particles. So if this is the gold foil and I throw alpha particles, what should happen? It should bounce back, right? Why? Okay, it's not a tough question. Why did it bounce back? What is that? It's a wall. A wall is what? Solid. Thank you. Okay. So that's what you would expect. But when he did it, most of the alpha particles went right through the foil without being deflected. And there's the experiment. So most of them went through. So he deduced correctly that most of the atom is empty space. Here's the nucleus. So the alpha particles that don't hit the nucleus just pretty much go right on through. So the majority of the mass is located in a small, dense region. So these were some models of the atoms. So we have a positive charge spread throughout the entire sphere. And the sphere is positively charged. This is the more recent model where we have a densely positively charged nucleus and a region of mostly empty space where electrons reside. So Rutherford's atom, tiny, dense, positively charged nucleus of protons surrounded by electrons. How do we describe the relationship of electrons to each other in the nucleus? We use the measurement of particle energy rather than position. So you've all probably seen a fan, right? You got the blades. When it's in the off position, you can stick your finger in between the blades, right? No problem, because it's mostly empty space. Turn the fan on high. Let's see you stick your finger in there. Go away, whoever this is. All right. So, but still mostly empty space. What is going on now? It's spinning so fast. So even though it's mostly empty space where the electrons are, how fast do electrons travel? Speed of light, very fast. So essentially, even though as it's going around the nucleus, it's going so fast it's like it's there, right? Like it's almost a solid object. So to understand atomic structure, we have to understand light. So spectroscopy is absorption or emission of light by atoms. We use that to understand electronic structure. you have to understand light, electromagnetic radiation. Travels in waves from a source. Speed of 3.0 times 10 to the 8th meters per second. Fast. Light is propagated, moves as a collection of sine waves. Wavelength is the distance between identical points on successive waves. So here we have a wave moving down this way. It's called propagation. If we measure from peak to peak, that's the wavelength. Each wavelength travels at the same velocity, but it has its own characteristic energy. So if I put a point right here, every time a wave peak passes, I can time it. So for every 2 that goes by here, how many go by here? Oh, this one. 1, 2, 3, 4, 5, almost 6. So this one, the bottom one, is a shorter wavelength, has a higher frequency. The longer wavelength has a lower frequency. So now, this is a low frequency. If I get to a higher frequency, which one has more energy? The higher frequency. So if we look at the electromagnetic spectrum, this little part right in here, the visible one, is the one we see. And you all know the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Remember him? If we go to the ultraviolet, notice the wavelength is getting smaller. The energy is getting larger. So ultraviolet, what do we use that for? UV. UV light? What? What'd you say? The sun? Yeah, but I mean, what do we use it for? Well, not so much heat, but we use it to destroy bacteria on that. You go and see different areas, you see those UV lights. We go even lower wavelength, higher frequency, we get X-rays. Okay, obviously X-rays go through our skin and that's stopped by bone. Higher energy, even lower wavelength, we get gamma rays. Gamma rays go through everything, except maybe lead. So you're getting hit by them right now. Sometimes they're called cosmic rays. If I put a Geiger counter on the counter, you'll hear it clicking from cosmic rays coming through the building. Can't avoid them. Yes. And out further. Go to the other side, we go to the infrared. Less energy. Now, infrared, those are your heat lamps. Not your tanning lamps. Your tanning lamps are UV. By the way, tanning lamps aren't any safer than being in the sun. UV is UV. Getting even longer wavelength, lower energy, you have your microwave. This is a full wave, this is a microwave. Okay. Longer wavelengths, you have your radio frequency. Your FM and then your AM. Okay. So I know you've all seen a rainbow. What's the top color on the rainbow? Red. And the bottom color is violet. So which one is the longer distance from point to point? The red. So it's the longer wavelength, it's the lower energy. So atoms can absorb and emit energy by promotion of electrons to higher energy levels and relaxation to lower energy levels. So here I am, I'm an electron, I'm standing on the ground, i.e. I'm in the ground state. I'm too old for this. Okay. Oh, okay. So now I'm up here. To get up here, I had to absorb energy, right? So I absorb energy. If I jump off of this, can I stop halfway down? No, I have to go all the way down. So it's one level or the other. Now, when I jump down, I'm going to release energy. Like if you laid down underneath me and I jumped, there's some energy released, okay? So that's the relaxation. Because I only have choices of 2 levels, those are called quantum levels. So if you study physics, there's Newtonian physics, which is macro scale, and there's quantum physics, which is atomic level. So there's specific levels. Think of it as the difference between digital and analog. You know the difference between digital and analog? If you look at a clock, like if you look at the clock on the wall back there, the second hand is going between each second. That's digital. If you have an old watch and hand is sweeping, that's analog. It's not distinct packets. Digital TVs are much sharper because you have pixels, so you just get the little squares. The old CRT analog TVs, picture wasn't as clear, it was blurry because the energy would leak out from the sides. Well, the higher energy levels are promoted, and you come back to the relaxed state. Spectral lines are a result of electron transitions between allowed levels and atoms. So there's only certain levels that are allowed. So to go from the ground state to a certain level, you have to absorb energy. When you relax, you release that energy. That energy is released as a certain wavelength of light, depending on how far and how much energy. So here, if you see hydrogen has 1 electron, it has only certain levels it can go to when it gets excited. When it comes back, it releases energy, and if you look in the visible region, you see an orange, a blue, a bluish green, a blue, and a violet. Helium, 2 electrons, you get different combinations. You get the 2 oranges, a yellow, a green, and a blue. Okay? So we can actually show you this. And we're back. And we're just looking at hydrogen now. So electrons exist in fixed energy levels surrounding the nucleus. That's called quantization of energy, quantum levels. When we promote one, it absorbs energy. That's the excited state. When it goes back to the ground state, it's called relaxation, and it emits a photon of a certain wavelength, depending on where these levels are. So you have energy levels 1, 2, and 3. You can imagine it takes more energy to get to 3 than to 1. So when it relaxes from 3 to 1, it's going to give you more energy out. So you can see the combinations. You can go from ground state, or you can go from 1 to 2, then 2 back to 1, 1 to 3, 3 back to 1, 1 to 3, 3 back to 2, 2 back to 1, 2 to 3. So there's several different combinations. And they all give different wavelengths. So the amount of energy absorbed is a precise quantity because of certain levels. So Bohr called what was between the levels, orbits, and ground state was the lowest possible energy state. You may have a term someone described as being well grounded. That means that they're usually like calm and not very high energy. So his theory, a lot of levels are quantized energy level orbits. Electrons are found only in these energy levels. The highest energy orbits are farther from the nucleus. Then he said, atoms absorb energy by excitation of electrons to higher energy levels and release energy by relaxation of electrons to lower energies. And we can calculate the energy difference by the wavelength emitted. So we can look at those spectral lines and go back and calculate the energy. We're not going to do that here. That's probably 151. However, when he went to atoms with more than one electron, it failed to explain the line spectra. Bohr's atom theory used orbits. Modern theory, electrons do not orbit the nucleus. An orbit is a two-dimensional. Planets orbit the sun. It's a two-dimensional thing. We have what's called orbitals, regions in space with a high probability of finding an electron. Electrons move rapidly within the orbital, giving a high electron density. So what does that mean? If I said to you, you're going to go in this room. In this room, there's a light bulb in the middle, nothing else, and a moth. The light bulb is on. Where's the moth? By the light bulb. Okay, if you ever had a moth in your house or similar insect, you know, it's about, you see it fluttering on the light. Is it unusual to see it over on the wall somewhere? No, I mean, you can see it on the wall somewhere. I'm sure it gets tired and that. But the high probability is going to be by the light bulb. And not just in any one spot. It flutters all around. Well, the electron does the same thing. If you think of this as the nucleus, an orbit would mean it just goes on one track. This forms a cloud. So it goes this way and this way and this way and sideways and upways and long ways and short ways and all the way around. But it's within a certain region, and that's called the electron cloud or the density, electron density. They calculated that using something called the Schrodinger wave equation, higher level calculus. No, you won't have to do that. And later on, we will work on how to do stuff. Boy, we're going fast through this. Am I going too fast? Yeah, no. We'll find out. So Mendeleev, we'll get back to the periodic table, and Meyer noticed that as you list elements in order of atomic mass, there's a distinct regular variation of their properties. In other words, it's periodic. Hence the name. Periodic law, the physical and chemical properties of elements are periodic functions of their atomic numbers. So here's the periodic table. Now, if you took chemistry in high school, I know one of the favorite things for the chemistry instructor to do is have you memorize the periodic table. Don't bother. It's a waste of time. You have one. Learn how to use it. It's a map. So right here, even though it's color-coded, if you look at this little staircase here at boron and going down through aluminum and silicon, germanium, arsenic, antimony, tellurium, and polonium, right there. Everything from this blue, this dark gray, and this purple are metals. Everything on the other side, these yellow, are nonmetals, and hydrogen's a nonmetal. The green ones, actually, let me move this down now, are metalloids. So right away, if I give you an element, you should be able to tell me if it's a metal or a nonmetal, just by looking at the periodic table. We have at the top here the numbers 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A are called the main group elements. They behave nicely with all the work we're going to do. Between 2A, we make a transition to 3A. Therefore, these, the B's, are called the transition elements. Down here, you see a little gap between lanthanum and hafnium. It goes from 57 to 72. All of these fit in there. These are called the lanthanides. Similarly, between actinium and ruthenium, we have the actinides. They're down there for a couple reasons. One, it makes the table more compact. It fits nicely on a sheet of paper. And later on, you'll find out why else they're down there. So right away, you've learned a lot about all the elements. You probably know a lot of them offhand. C is carbon. Na is what? Sodium. Isn't that obvious? Na, sodium. Natrium, Latin. Si is what? You better say silicon. Silicon is something completely different. Has different uses. Weather stripping. Silicon is a metal. Oid. Fe is iron. All right, there's multivitamin iron supplements from women called Slow Fe in that. Okay. Cu, of course, is it's copper, because Co is cobalt. K, of course, is potassium, right? Potassium begins with K. Okay. W is Wolfram, is the German. Tungsten is W. I do the ladies' favorites. Au is gold. Ag is silver. Pt is platinum. I always say the ladies, gold, silver, platinum. Okay. Pb is Latin plumbum is lead. Think of an occupation that sounds like plumbum. Plumber. That's how they got their name, because most of the pipes in the early days were made of lead. And if you're in Flint, Michigan, apparently that's still the case. Okay. So as the periodic table was formed, people, whatever was in fashion at that time, that's how they got their names. When you get to the Artificial ones, we have americium for America, californium for California, berkelium for the University of Berkeley where it was made. Then we went through scientific names: einsteinium, fermium, mendelevium, nobelium, lawrencium. Seaborgium, Glenn Seaborg was a scientist who made a lot of the artificial elements. Of course, we have planets: uranium, neptunium, plutonium. So usually who discovers it gets to name it. They got some new ones now. So the rows are called the periods. They contain 2, 8, 8, 18, 18, and 32 elements. The groups are the columns. They're also called families. Elements in a particular group or family share many similarities as in a human family, I guess. NaCl is sodium chloride, salt. So people with high blood pressure have to avoid sodium. So they take a salt substitute. Anybody know what the salt substitute is? And I'm not talking about Mrs. Dash herb mixture. I'm talking about if you go to the store where they have the salt and they have the salt substitute, it's what? Okay. It is potassium chloride. Notice on a periodic table where sodium and potassium are. They're in column 1. Potassium's right underneath sodium. Same group, similar chemical properties. Notice NaCl, 1 sodium, 1 chlorine. Potassium chloride, 1 potassium, 1 chlorine. If I was going to make rubidium chloride, what would its formula be? Rb. Take a wild guess. If this is this, this is this, what would rubidium chloride be? RbCl. Because they're in the same group, they're going to react the same way. So again, the periodic table tells you a lot just by looking at it. Well, it's a nonmetal, yeah. It's a little bit different. Hydrogen really shouldn't be over there, but they put it over there because just one. So metals, elements tend to lose electrons during chemical change, forming positive ions. Nonmetals tend to gain electrons during chemical change to form negative ions. So we said sodium was a metal, so it loses electrons, it becomes positive, Na+. Chlorine's a nonmetal, it gains electrons, it becomes Cl-. What do positive and negative particles do? They attract. That's how you end up with sodium chloride. Later we'll find out how that works. And again, by looking at the periodic table, it becomes very easy to figure out how those things go together. So the metals, we said, are primarily on the 2/3 left side of the table. What are properties of metals? If you haven't figured this out, high thermal and electroconductivity, which is why we cook with them and why we use them for wires. High malleability and ductility. Malleability is the ability to be pounded into thin sheets. You've seen gold leaf and that, very, very thin. Ductility is the amount to be able to stretch, hence we can make wires out of them. Metals have a metallic luster. Ooh, shiny, okay. And they're solid at room temperature, except for one. Give me a metal that's not solid at room temperature. Mercury. Nonmetals form negative. They're the right 1/3 of the periodic table. They tend to be brittle. You think of charcoal, it's kind of brittle. Powdery solids are gases. So charcoal we can grind up. Sulfur is a yellow powder. Think of the gases. You can think of oxygen, nitrogen. They're obviously gases. Their properties are opposite of metals. They usually don't conduct electricity well or heat. So we said the atomic number was the number of protons in the nucleus of an atom of an element. And they give the nuclear charge or positive charge from the nucleus. Most periodic tables give the element symbol, the atomic number, and the atomic mass. The one in your book. And when you do the homework, please use the one in your book if you've gotten someone from somewhere else. Because if you look in your book, you're going to see the numbers are slightly different than the ones we have posted on here. These go out to more places. I think your book lists oxygen mass as 16. What is this one lists as 15.999? So there you see the symbol. Some of them will put the name on them. But your periodic table, I think, is in the back of your book. Well, no, there's one whole one in the back of the book, I believe. It's in the back. Or yeah. So there's the other side of that table. There's a table, blue table, and then there's the periodic table. So the periodic table's in the back of your book, and on the opposite side is a table that has them all in alphabetical order. So if you can't find it on the periodic table, flip the page over, look on the table, find it, it'll tell you the atomic number. And then you can go back and find it on the periodic table. So, P is what? It's phosphorus. What group and period is it in? What? No, what group? Give me the group number. The Roman numeral one. 15 is Arabic numeral. Roman numeral is the other one. What did you say? VA? 5A. So that's the group. What period is it in? Period 3. 3 is the row. 5A, 1, 2, 3. Okay? So chromium. Where's chromium? Here. What group's it in? 6B. What row? 4. Period. Element 30. What is element 30? Zinc. Groups it in? 2B. Or not? 2B. And period 4. elements are found in period 6? Well, you can't count. Don't look up here because you got to take the purple ones out, the pink ones out. 6, 7, 8, 9, 10, 12, 13, 14, 15, 18. No, you don't count the ones at the bottom. So 18. 18. How many elements are in group 5A? Yeah, 18. 6. 5A, we got 1, 2, 3, 4, 5, 6. So everybody should be able to navigate around the periodic table. Okay, electron arrangement in the periodic table. I'm going to stop here because I don't want to get halfway through it and confuse everybody. So